10% is the minimum annual increase in value for a specific type of plastic toy, a figure that consistently outpaces the growth of both gold reserves and the traditional stock market. This specialized asset is the Lego brick. Why do these small components carry such remarkable financial weight in the global economy? At first glance, they look like simple children's playthings, but in reality, they are high-precision industrial products with a secondary market value that rivals precious metals. The process of understanding this value begins deep within the manufacturing infrastructure. One can notice how the production cycle initiates with the arrival of raw plastic granulates in massive silos. Why does the company maintain such a rigorous design philosophy across its entire history? The answer lies in the universal coupling system that ensures every single brick produced today remains compatible with those manufactured 5 decades ago. The machinery operates with a precision measured in micrometers to guarantee this mechanical continuity. Everything only gets more complicated as the raw materials transition into the molding phase. High-pressure injection molding machines exert tons of force to transform the heated plastic into familiar geometric shapes. The equipment gradually feeds the material into molds where it is subjected to intense heat and cooling cycles. It is visible how automated sensors monitor the exact dimensions of every stud and tube to ensure the tolerances do not deviate by more than 1/1000th of a millimeter. But this is just the beginning. The factory floor functions as a synchronized ecosystem of robotics and pneumatic systems. Manipulators move with calculated speed to sort and package the finished components. The process is only gaining momentum as thousands of bricks per second flow through the assembly lines toward the final quality control stations. The material is ready to move to the next processing phase without haste. 7,500 pieces of plastic are not what truly defines the market value of a premium construction set. Why does a collection of interlocking bricks often appreciate faster than traditional financial assets? At first glance, the price should depend on raw material costs or the sheer quantity of elements, but in reality, the valuation is anchored deep within the realms of collective memory and cultural fandom. One can notice how the demand for specific models shifts once they are no longer found on retail shelves, signaling a transition from a simple toy to a rare collectible. But this is just the beginning. Nostalgia acts as a primary catalyst for growth in the secondary market. The sets that consistently demonstrate the highest appreciation are almost exclusively linked to vast cultural universes such as Star Wars and Harry Potter, or sophisticated lines like modular buildings and Creator Expert. The process is only gaining momentum as these adult-focused kits become centerpieces for investors. It is visible how the market reacts when a production run ceases. The sudden scarcity triggers a price surge that reflects the emotional weight of the brand. It only looks obvious that size dictates cost, but the reality is more complex. The Millennium Falcon from the Star Wars Ultimate Collector series stands as the most prominent example of this economic phenomenon, holding the title of the most expensive set ever officially released. It is visible how the extraordinary level of detail across its massive hull transforms it from a toy into a global cultural icon. Collectors are not merely acquiring 7,500 individual pieces of molded plastic. Everything only gets more complicated when considering the intangible value of the Star Wars legacy itself. The transaction is fundamentally an acquisition of history and shared experience. Buyers pay a premium for the physical manifestation of a cinematic legend that spans generations. This emotional connection ensures that the value of the object remains independent of the original production costs. The material reaches a status where it is no longer defined by its physical weight, but by the rarity of the memories it represents. Thus, the journey of the brick evolves from a simple assembly process into a high-stakes preservation of cultural artifacts. 28 tons of raw plastic granulate arrive at the factory gates inside specialized transport trucks to begin the manufacturing journey. Why must the production of these elements start with such rigorous material preparation? It would seem that any industrial plastic could suffice for a simple toy, but without selecting a specific engineering-grade polymer, the blocks would lose their ability to fit together perfectly across different generations of play. Virgin acrylonitrile butadiene styrene, commonly referred to as ABS, is the exclusive material of choice for these components. This specific grade of plastic is utilized because of its high structural strength, notable elasticity, and an innate ability to resist shrinkage or deformation over several decades of constant use. At first glance, the raw material appears as simple rice-sized pellets, but in reality, these granules possess an extremely high level of purity required for precision molding. The process is only gaining momentum. One can notice how powerful systems of compressed air blow the plastic granulate into tall storage silos rising high above the facility. From these massive containers, the material is not immediately processed, but remains in temporary storage until the production line below is ready to receive it. Every individual batch must first undergo rigorous laboratory testing to verify moisture content, chemical behavior, and color consistency before it is granted approval to move forward. Long winding networks of pipes transport the granules throughout the entire factory once they leave the silos. The material moves continuously inside these pressurized pipelines, traveling deep into the heart of the facility where the injection molding area is located. It is visible how the plastic granules flow downward through the tubes, eventually feeding directly into the specialized machines that will handle the shaping process. It gets more complex further on. Proprietary formulas that have been standardized for decades are used to begin the critical color blending phase. Raw plastic pellets are thoroughly mixed with concentrated pigments at this early stage to ensure that the hue is evenly distributed throughout the entire volume of the material. Because an uneven mixture would result in visible streaks or structural weaknesses, the blending must be absolute before the thermal processing begins. 50 different colors are currently produced within the factory, ranging from vibrant primary tones to specialized shades. Each individual color is tightly controlled by automated systems to maintain total stability and consistency across every production batch. At first glance, the variety of colors seems like a simple aesthetic choice, but in reality, it requires precise chemical balancing to ensure every brick matches its predecessors perfectly. One can notice the uniform distribution of the pigment as the mixture prepares for the next stage of transformation. The material leaves the blending area, transitioning into a calm stage of readiness for the high-pressure molding cycle. 440 to 590 degrees Fahrenheit is the thermal range required to transform solid plastic into a workable molten state. Why must the temperature be maintained within such a narrow window? The semi-processed material flows directly from the color blending stage into the injection molding area, which serves as the central hub of the entire facility. Any fluctuation in heat would compromise the toothpaste-like consistency of the melt, preventing it from behaving correctly under the immense forces of the machinery. The injection process occurs under extreme pressure. One can notice how the molten plastic is driven into steel molds with a force of 29,000 pounds per square inch. This massive pressure ensures the material penetrates every microscopic corner of the predefined shape without leaving air pockets. If the factory needs to introduce a new element, the entire steel master template must be replaced, as it alone determines the final geometry of the brick. But this is just the beginning. It only looks obvious that the plastic needs time to cool, but in reality, the solidification happens almost instantly. The camera glides along the molding units where the hot liquid meets the cold surface of the steel. Within just a few seconds, the material locks into a rigid form. The mold then opens in a steady, controlled rhythm, releasing the newly formed pieces like individual prints from a high-precision press. Before moving to the next stage, every unit undergoes a rigorous initial round of inspection. It gets more complex further on. High-resolution optical sensors scan each brick from every possible angle to verify its flatness and the precision of its connecting features. One can notice how the system detects minute deformations or surface scratches that are completely invisible to the human eye. Any part failing to meet these strict criteria is immediately diverted from the line. These rejected components are not discarded, but are instead collected and ground down to be recycled directly within the plant. Approved bricks are then transferred into an internal transport network managed by autonomous robots. Automated Guided Vehicles, or AGVS, have navigated these predefined routes since 1987. When a container beside a machine reaches its capacity, a robot approaches to remove the full load and replace it with an empty one. The full containers are carried toward the central conveyor system for further processing. Each bin is marked with a unique barcode, allowing the central computer to track the exact quantity type and location of every production batch across the entire facility. Why is the recycling process kept entirely within the factory walls? Surface logic might suggest selling the scrap, but the factory operates as a closed loop to preserve the absolute purity of the raw materials. By grinding and feeding rejected parts back into the production line, the facility minimizes waste while ensuring that recycled content does not degrade the final product quality. Only the components that satisfy every technical standard move forward to the decoration line. Everything only gets more complicated as the plastic gains a soul. This phase involves the mechanical assembly of heads, torsos, arms, and legs, alongside the application of intricate patterns. Facial expressions and logos are not applied as decals or painted by hand, but are instead created through a process known as ultra-precise tempography. A soft rubber pad picks up specialized ink from an etched plate and presses it onto the plastic surface, transferring the image with the accuracy of a fingerprint. To maintain consistency, robots rotate the components beneath the printing heads with timing synchronized down to thousandths of a second. High-speed inspection cameras monitor the output for any misalignment. Even an ink line that deviates by as little as 4/1000ths of an inch will trigger a rejection. Once printed, automated machines fit each arm into its shoulder joint and mount heads onto necks with mechanical precision. The finished minifigures and bricks then leave the decoration area and enter the storage and sorting stage. Here, the parts are placed into containers and gently shaken to optimize the available space before being sealed and labeled. The containers are then moved into a high bay warehouse where storage racks reach a height of 121 feet. At first glance, this looks like simple storage, but in reality, it is a dynamic sorting environment. Automated counting systems weigh and measure every individual piece to confirm the batch configuration. All positioning and retrieval operations are managed in real time by a central system to ensure that every brick, even those manufactured decades apart, will achieve a perfect clutch fit. The packaging line operates at a relentless pace. Once the bags reach the correct quantities, they are combined with instruction manuals and placed into boxes following a programmed sequence. Automated systems erect the cardboard structures, load the contents, and perform a final check before sealing the lids. On the highest capacity lines, the factory completes over 50,000 boxes every 24 hours. Each package is secured and marked with data codes that record the entire history of the production batch. The finished sets are then moved to the master packing area for global distribution. One can notice how automated systems group the products based on their outbound routes before placing them into impact-resistant shipping cartons. These cartons are stacked onto wooden pallets and wrapped in multiple layers of protective shrink film by specialized machines. From the factory floor, the shipments travel to logistics hubs via truck or ocean container to reach more than 140 countries. Through this coordinated supply chain, the facility maintains a consistent experience for consumers worldwide. A finished toy represents a system of remarkable industrial precision and complexity. While these plastic elements are highly valued, other common objects, such as the humble pencil, involve manufacturing processes that are equally intricate despite their lower cost. The material is ready to move to the next processing phase without haste. 100% of the journey for a professional-grade pencil begins far from the sterile environment of a factory floor, originating instead in the depths of managed forests. Wood serves as the structural backbone of the entire instrument, providing the necessary rigidity and protection for the fragile core. To ensure long-term stability and a clean aesthetic, manufacturers select soft woods characterized by straight grains that resist warping and remain easy to cut. The most prized species among these is California incense cedar, chosen for its resistance to cracking and its capacity to maintain its physical shape during the drying process. Why is this specific timber harvested with such extreme care? At first glance, it may seem like any other logging operation, but in reality, these trees come from strictly managed farms where every single trunk removed is replaced by a new sapling to maintain a sustainable supply chain. Logs are cut into uniform lengths and loaded onto specialized trucks destined for the milling facility. But this is just the beginning. Once the cedar arrives, the raw material undergoes processing with near-perfect technical precision to transform round logs into workable components. 1 millimeter is often the margin of error as specialized saws slice the timber into thin sheets known as slats. Each of these wooden plates measures exactly 5 to 6 millimeters in thickness, which is the precise dimension required to form 1/2 of a pencil body. It is visible how the equipment gradually feeds these slats through an inspection zone where sensors and trained technicians scan for defects. Any sign of warping, knots, or surface cracks leads to immediate rejection, as these flaws would compromise the integrity of the final tool. The slats that pass this rigorous screening move forward to the grooving stage. A milling machine carves a series of shallow, parallel channels along the entire length of the wood. One can notice how the placement of these grooves is executed with jewelry-like precision. Why is the alignment of these channels so critical to the final product? The groove serves as the permanent home for the graphite core. If the channel is even slightly off-center, the core will likely break during sharpening or under the pressure of daily use. After the grooves are cut, the equipment applies a microscopic coating of oil or wax to the surface. This treatment protects the wood from moisture while providing a smooth texture that facilitates cleaner assembly in the upcoming stages. Everything only gets more complicated from here. 2 primary ingredients form the soul of the instrument: graphite and clay. Graphite is a crystalline form of carbon composed of layered structures that allow it to glide smoothly across paper surfaces. This mineral is primarily extracted from open-pit mines located in countries such as China, Brazil, India, and Mozambique. When a natural vein is discovered, heavy machinery or controlled detonations are utilized to break the ore away from the surrounding rock. One can notice how the raw material is then transported to refining facilities to remove soil, stone, and trace metals. The objective is to achieve a purity level exceeding 90%, which is the minimum standard for industrial cores. The quality of this graphite determines the smoothness, sheen, and durability of the stroke. The process is only gaining momentum as the purified powder is blended with clay to create a structural binder. Why is the ratio between these two materials monitored so strictly? It looks outwardly simple to mix these powders, but in reality, this balance defines the hardness grade of the pencil. A higher concentration of clay results in a harder, lighter core known as an H grade, while more graphite produces the soft, dark stroke of a B grade. Industrial mixers knead the mixture until it reaches a perfectly uniform consistency. The graphite clay paste is then extruded into long, thin strands that resemble dark spaghetti with a diameter of only a few millimeters. These delicate threads are dried to remove all internal moisture before being fired in kilns at temperatures ranging from 1000 to 1200 degrees Celsius. This intense heat treatment hardens the material and locks the molecular structure in place. Finally, each core is submerged in oil or wax to reduce friction during writing. Alongside these, factories also produce colored leads, which use pigments and fillers like kaolin or talc instead of graphite. Unlike their carbon counterparts, colored leads are never fired in kilns, as high heat would degrade the pigments and destroy the color quality. One single conveyor system brings the wooden slats and finished cores together to begin the final assembly. A grooved slat is placed onto the line with technical accuracy, and the cores are inserted into the channels either automatically or by hand. For premium lines with fragile cores, manual placement is often utilized to prevent breakage. A second slat, coated with a thin layer of adhesive, is aligned perfectly and pressed onto the first, creating a sandwich-like structure. The unit enters a high-pressure press where calibrated force ensures the glue spreads evenly. The block must then rest for a set period to allow the adhesive to cure fully, ensuring the core remains fixed at the dead center. Individual pencils are born when the bonded blocks are fed into automated cutting systems. Precision saws slice the sandwich into standard lengths of 17.5 centimeters. These rough sticks are then passed through a profiling machine to achieve their final shape, whether round, hexagonal, or triangular. After shaping, each unit receives between 3 and 6 coats of paint, starting with a primer and ending with a protective outer layer. Heat-curing systems ensure each layer adheres perfectly before the identity of the pencil is stamped onto the barrel. Hot stamping machines or metallic foil embossing apply the brand name and grade with a durable finish. One final detail remains for many models: the attachment of the eraser. This assembly begins with the creation of the ferrule, a small metal ring that connects the rubber to the wood. Automated machines press the synthetic rubber into the ferrule and crimp the entire unit onto the end of the pencil. The pressure must be strong enough to secure the part without cracking the cedar body. For retail-ready packs, the pencils may pass through a final sharpening station where a fixed blade carves the tip at a precisely calculated angle. After a final quality control check for straightness and paint uniformity, the tools are sorted into sets and placed into their respective packaging. From here, the finished product moves further along the production chain to distribution warehouses. The material is ready to move to the next processing phase without haste. 100% of the components in a standard pencil originate from a complex global supply chain spanning multiple continents and thousands of miles. Why does such a common object require such an expansive logistical network? At first glance, the assembly of wood and graphite appears elementary, but in reality, it represents a highly specialized convergence of disparate raw materials. California's cedar forests provide the aromatic and stable timber required for the outer casing. It is visible how the wood is sliced into thin, uniform slats to ensure consistent grain alignment. This is not the limit of the resource procurement. Graphite mines located across various regions of Africa and Asia extract the carbon core that allows the tool to function. But this is just the beginning. The raw materials are transported to high-speed production lines where machinery operates with millisecond precision to mill, groove, and bond the components together. One can notice how the equipment gradually applies layers of lacquer in a continuous automated stream. The process is only gaining momentum. Despite the presence of advanced robotics, several delicate steps in the finishing and quality control phases still rely on the nuanced perception of the human touch to identify imperfections that sensors might overlook. The manufacturing cycle demonstrates a balance between modern industrial speed and traditional craftsmanship. The finished writing instruments move along the final conveyor to be packaged for global distribution. Thus, the transformation of raw cedar and carbon reaches its conclusion, marking the end of a long journey from the earth to the hand.